Petroleum refineries transform crude oil into useful products such as kerosene, petrol, jet fuel and fuel oils. Throughout the course of history, waste management strategies have evolved from being non-existent to an end-of-product assessment to a fully holistic life cycle assessment.
Hello, my name is Steph and I'll be talking about the industrial processes, raw materials, waste streams and waste characterization. The industrial refining process can be broken into three basic categories. Separation involves crude oil being physically separated into fractions according to the hydrocarbon molecules. Conversion processes change the structure and size of the hydrocarbon molecules, and the treatment process aims to achieve the desired physical properties by changing the chemical nature of hydrocarbons. So petroleum is made up of crude oils and natural gas that formed millions of years ago and is extracted from below ground. The crude oil extracted is a complex mixture of hydrocarbons, chemical compounds composed of only carbon and hydrogen, as well as small volumes of other materials including nitrogen, sulfur and oxygen. Other materials used in the process include water and chemical catalysts. The waste streams produced in the refinery of petroleum can be categorized into gas, liquid and solid, and are often broken down further within those streams. So waste gases are dependent on the treatment process, however it usually entails controlling emissions of sulfur oxides, hydrocarbon vapors, smoke and smells. Waste water includes stormwater, processed water, cooling water and sewage. Processed water is contaminated as it has come into contact with the process streams, however it can undergo contamination and be used in areas of the refinery. So cooling water is the main use of water within the refinery. With limited contamination, it doesn't come into contact with the process streams directly, and it's often recycled throughout the system multiple times. So solid waste often depends on the composition of crude oil being refined and may contain heavy metals. Hydrocarbon wastes are dewatered and reprocessed for recycling, and spent catalysts are often recycled to manufacturers, chemically treated or landfilled. So following the identification of waste streams produced by the refinery, waste characterization should take place. And this is to determine the composition of the waste streams, which indicates how these streams should be handled, their transport requirements, and how they will be appropriately disposed of. So proper regulatory classification often includes identifying properties such as temperature, pH, total suspended solids, biochemical oxygen demand, etc., and more. So the results of the analysis determine the future of the waste, whether it be reuse, recycling, treatment, or whether the waste stream should be classified as hazardous in accordance with the local and or national regulations. So these classifications can often aid in determining what type of landfill is required for disposal or if pre-treatment is necessary.
First step in waste minimisation is identification and quantification of the waste streams. Minimisation opportunities present themselves at all stages of the refining process. However, acting upon the opportunities presented are often governed by costs and legislation. First step is the improvement of existing equipment and processes. Waste treatment systems and good practice can minimise waste as well as improve quality of waste streams, which reduces hazardous characteristics. All petroleum refineries should have their own wastewater treatment plant, as aqueous waste is produced in all stages of the refining process. All runoff channels and guttering should be directed to treatment for recycling and effluent disposal purposes. Segregated effluent streams decrease the difficulty of treatment and optimise water consumption, creating more efficient and effective treatment processes, meaning effluent may be able to be reused or disposed of if the levels are safe. Desalting stage produces high temperature salt water which can be directed to the wastewater treatment plant. Reducing turbulence in the desalting phase minimises sludge buildup and can also be reduced by precipitators and demulsifiers. An integrated system with reduced tankage is a key opportunity in minimising sludge. However, if tanks are used, mixers should be applied to mitigate solid settling. Catalytic regeneration reformers can be installed for in situ recycling of catalyst material, and catalyst fines can be recycled, reused in local civil applications.
Hello, my name is Naz, and I'm going to talk about identification of alternative waste treatment methodologies. So the first method is CO2, versatile acid alternative for pH control, which means we are going to use carbon dioxide instead of other mineral acid, for example, sulfuric acid or hydrochloric acid. So here, the carbon dioxide is dissolved in wastewater to produce carbonic acid. The carbonic acid is much safer and stable unlike other acid. It preserves the natural alkalinity and does not result in major fluctuations in the pH. Able to treat the wastewater up to 2,000 cubic meter a day in a normal oil refinery. So the next alternative method is the electrochemical AOPs, or EAOP in short. These EAOPs produce hydroxyl radicals. These hydroxyl radicals are actually the strongest oxidizing agent known to mankind. They can treat the wastewater up to 200 Fahrenheit and heavily reduces the cost compared to other traditional treatment processes because it requires less manpower due to fewer steps and control analytical testing. So the final alternative method was the dehydration and solvent extraction, or known as the Carver Greenfield process, where the waste is mixed with low-cost hydrocarbon and then evaporated for the indigenous oil to be extracted. The extracted oil then can be reused and recycled. Around 5,000 tons of waste can be treated at the refinery site, which eliminates the transport cost. And the process produces wet water and dry solid, which can easily be treated in any wastewater facility and disposed at any landfill according to BAT, which is the best available technique. So this is the part where we are going to choose the most appropriate waste treatment methodology. So why electrochemical AOP was not chosen, even though it had a lot of good feedback, because it is still an underdeveloped technology which needs much more improvement. Issues arises whenever the temperature of the wastewater reaches above 200 Fahrenheit, and on top of that, it loses its effectiveness due to the wastewater having a wide range of reaction species. Although it can be considered a very reliable technology in the future when it is fully developed, but not at the moment. So the most appropriate method will be the CG process and CO2 as an alternative for pH control together, because the combination will produce non-hazardous dry waste and can neutralize up to 20,000 cubic meter of wastewater per day. In addition, the extracted oil from the CG process can be recycled and reused, which is great for the environment. Despite the lengthy and complex process, the outcome of the both technology together can save a lot of money, and this is the best available technique that we have.
As mentioned earlier, all petroleum refineries should have wastewater treatment plants to treat aqueous waste streams. Hydrocarbon biodegradation by biological or chemical processes, along with reverse osmosis membrane units, can remove up to 90% of contaminants in waste streams. This water can be recycled or reused in different stages of the process. The effluent can then be disposed back into the environment or main sewers if it meets environmental parameters, as long as it is continually monitored. Any hazardous effluent streams that are removed from site by sucker trucks need to be tracked with correct documentation. Waste minimisation strategies can include vast infrastructural investments, revolutionary methods, or simple operational and practice improvements. The automation of the industry has seen a reduction in over 80% of oil spills, which had previously been attributed to human factors. The automation of VOC-run UK refineries presents a very good example of the role of autonomy in industry, with the autonomous pH adjustment of over 20 megalitres of wastewater per day to suit the fluctuating 6-hourly tide, reducing the concentration of discharge and the impact of the effluent on the environment. A possible innovation process to reduce waste production is the extraction of remnant oil from wastewater using biological means. Studies undertaken as early as recently as February this year have shown the possibility of high organic concentration oily sludges to be converted into viable high-grade bio-oil. Within the study, the high organic sludge at 70% weight to volume ratio within a 96-hour test converted the sludge into a bio-oil of similar heating value to subbituminous coal. Subbituminous coal powers 41% of the US. This proves the potential of it as a valid power resource. Fluid catalytic crackers, or FCCs, are a crucial aspect of modern refining practices, representing 831 kilotons of use last year with a market cap of $2.9 billion. However, the emergence of new unconventional feedstocks from Canada and Venezuela require alternative processing methods in order to maximise product and reduce waste. The creation of new catalysts such as ZSM5 will help industries cope with the heavier, more aromatic molecules they will exhibit with these new feedstocks, as well as producing more polypropylene for future demand, decreasing waste. Moreover, not only will new catalysts be required, but changing attitudes towards the use of spent catalysts, where over 11,000 tonnes per day discarded. This stream could be minimised by reuse of the catalysts, recycling of the catalysts, or the use of catalysts in external injuries, such as the formation of cement, or their reuse, as in studies undertaken in India, which have shown a 95% rehabilitation rate for catalysts. The use of catalysts as a cement additive is a very, very important step, with the cement industry producing over 6% of the world's total CO2. The addition of catalysts have actually shown in the long run to increase the strength of concrete, while also decreasing its demand for cementitious material. This combination of both industries is a tertiary and holistic way of looking at waste minimisation, not only in the petroleum industry, but also in the cement industry.